Morning, guys. So over the last few days, we've been looking at developing this new model. Essentially, how the Bohr model doesn't quite give us a complete picture. The Bohr model is actually only able to show us our s electrons and p electrons as our valence electrons. As you start entering those orbitals, the d orbitals, the f orbitals, those highest energy orbitals, they're actually inner electrons. As we do some practice with configuration here, in today's lesson, I just want to introduce to you what the electrons are actually doing if they're not actually in orbit and circling around the nucleus. And we're going to flip to a simulation later on to actually see what some of these shapes actually look like. So let's just do some practice here. You will be asked to do both full configuration as well as simple configuration. So while I have the periodic table, let's see if we can write the full electron configuration. So write the full listing. Let's do the configuration for chlorine. Right. So you can actually check what should the very last electron be. Chlorine is sitting right here. It's row number 3. It's in P block. It is the 5th element in, so therefore it should end in 3p5. However, for full, it means you want to build up from the lowest energy first. So from the lowest shell here, hydrogen and helium would have been 1s1, 1s2. So chlorine's configuration 1s2, 2s2 for lithium and beryllium, boron all the way through neon 2p6, sodium and magnesium would be 3s2, and then up to chlorine here would actually be 3p5. So that's just chlorine. Chlorine's normal charge as a halogen is it tends to gain electrons, it gets reduced, its charge goes down. And what happens is the chlorine actually ends up forming a chloride ion, Cl-. For anions, what we found here was the electron just adds to the next lowest energy spot. While all these other shells are filled up, let's just fill up that last shell here, chloride would actually be isoelectronic with argon. Right? So for anions, you just add them to the next lowest energy spot here. Sorry, I guess for full electron configuration, I guess I need to write out the whole thing again. 1s2, 2s2, 2p6, 3s2, 3p6, which if I did simple, that is isoelectronic with argon. It's basically the same look as argon would have as 18 electrons. For simple configuration, what we did is we started using the noble gas to hide any inner shells, especially as you get down lower on the periodic table. I don't always want to start from hydrogen, or else the list is going to get super long. Those electrons are core electrons, they just come along for the ride anyways. So what we started doing is we used the noble gas to hide the inner shells. Noble gas here with the exception of helium, which is just 1s2, because I would put the helium on the second column here. Neon down through radon here is all ends in p6, 2p6, 3p6, 4p6. You can look for the last p6 to hide any inner shells, and we're going to go square bracket with the noble gas, and that hides the inner shell for you. So let's do, for example, let's do niobium. So niobium here is going to be element 41. If I want to do the simple configuration, I want to hide as many shells as I can. So let's just backtrack here. Niobium is technically row number 5. So you just sort of look backwards here. Krypton here would actually hide the 4 inner shells niobium has. If I asked you for the simple configuration for niobium, you'd say niobium has everything krypton has, square bracket krypton, plus a couple extra. It has rubidium and strontium, so I'm going to say 5s2. Remember, niobium here is a transition metal. This is D block. For a memory aid here, the first row is 1 row shorter, so 4s is 3d, 5s is just 4d, and niobium here is 3 electrons in. We don't quite have those f's, so I don't have that complexity there, but this one here definitely 4d3. Right? So that's this simple configuration. Simple configuration does charges really well. So if niobium, let's say niobium became niobium plus 2. As I lose electrons, remember our rule was we remove p first, then s, then d, then f on the valence shell, on the outermost shell. Like layers of an onion, you can't tackle, even though I have 4p, 3p, 2p inside, I can't touch any inner layers until this outermost layer is gone. So I don't quite have my 5p's yet. Those are effectively gone. The 2 electrons I'm going to pull off first are going to be my s electrons. If I remove the 5s2, niobium plus 2 would be basically krypton still with a 4d3. And then for niobium here to become even more charged, because the d electron here is an inner electron, we're going to find it can lose any number of electrons. It doesn't need to be completely full to be stable or completely gone to be stable. So let's say it just became niobium plus 3. So I just pulled off one more krypton. Well, I don't have the S's anymore. So 4d2, that might be a stable anion. On your data booklet, you actually have written for you some of the charges for the 3D metals. Remember, the left-right order doesn't matter. IB would typically prefer having the 4D actually before the 5S. So niobium here, let me just write the really ending of it. So the ending of krypton would have ended off with, let's say, 4p6. Oops. So krypton would have ended off here with a 4p6. I would have wrote down, well, I'm filling in the next shell, 5s2, and then I'm starting going to 4d3. What IB would typically do is it's actually going to put the 4d here in front. And in that case there, at least all your p electrons are sort of, all your energy level 4 electrons are all together. The left-right order didn't matter because I still see the 5s is full, but the d's are still constantly being added. If you do IB's way and sort of putting all the energy level 4 ones together, you don't necessarily need to memorize this order. Remove P, S, D, F. You can actually rephrase it as you can say, remove the highest energy electron first. And if you have all the energy levels lined up perfectly here, the highest energy will be the one that's the rightmost. I don't quite have my 5Ps yet. Yep, the 5S's come off next, and then comes the 4D, and you slowly work your way that way. We won't get to charges that are more than about +7 or so. Usually by then you've completely lost the shell, and that's sort of the maximum charge we would handle anyways. When I say remove the highest energy first here, that sounds strange because if you did your energy level diagram, the whole reason why we actually started filling in 5s, the reason why that was filled up before 4D was because it was actually lower energy. Just because I moved left and right, I said it didn't change anything. Why is this one here highest energy first? Just a technical note here. Turns out the energy spacings, when you actually put electrons in, by the time the atom actually forms, this shell here actually ends up lower energy than the 4D. So especially when it comes down to actually losing electrons, we do actually pull it off highest energy first. So either put all the energy levels together and then just remove it right to left, or memorize this order here, P, S, and then D and F. We're going to come to the reason in this lesson here. The P and S electrons, those ones here are tracked by the Bohr model. These ones here are considered your valence electrons. These are your outer electrons, but the D's and the F's are actually inner electrons. They also have really weird shapes, but spatially speaking, they're actually really close to the core. So just to give you some understanding here, well, we've been using the S, P, D, and F just as placeholders. What do these ones here actually look like? What are electrons actually doing? You can switch over to actually watch the Big Bang Theory clip. It's basically Sheldon trying to explain the Schrodinger cat analogy that we're going to run into. And then you can come back and then we'll keep talking there. So we're going to look at a guy here called Heisenberg uncertainty. We're just going to get a quick taste of this one here. I just want you to be able to appreciate what each of these rooms look like. Okay, what are these orbitals if electrons aren't orbiting? From Heisenberg's uncertainty from his studies, he ended up with a conclusion that the position, and he used the word momentum. If you're in physics, momentum is related to velocity, so we'll just frame it as velocity. The position and the velocity of electrons cannot be known simultaneously. You can't know the whereabouts an electron is, as well as its momentum, its speed, its direction. You can't know both of them simultaneously. Now the question here is, well, why not? Couldn't I come up in the future with a better experiment, better technique? This is something fundamental in our universe. There's a fundamental uncertainty. There's a fundamental unknown in your universe. You'll definitely run with this with TOK. Well, there's an inherent lack of knowledge. But in our case, more specifically here, just a picture. Let's say I did an experiment. I wanted to ask this question, what are electrons actually doing around the atom? So far, we started with the Bohr model. We had sort of our nucleus. We had said, based on our absorption and emission studies, electrons can be in any number of shells. Electrons want to be in the closed shell if possible. what Heisenberg's uncertainty is saying here is, let's take an electron, let's say on shell number 2. If you do an experiment and you try to find out exactly where that electron is at that point, you can do an experiment and you can say, aha, I put my finger on it, I've localized and I've located my electron here. Turns out because of this Heisenberg uncertainty, the better you know this electron, the worse off you know the velocity. You might be able to take a picture and you might say, aha, I can see it, right? I put my finger on it. But in this case here, the better you can point where it is, the less I know what it's doing. It could be zipping this way, it can be zipping that way, it can go in this way, it can go any which way here. It actually becomes a question for what the velocity is. Let's do another experiment. Let's say this time I don't care about the whereabouts it is, I just want to track what the electrons are doing. Are they actually in orbit or not? So let's say I do an experiment and sort of out of my peripheral vision, I see an electron zip by. Oh, it went in that direction, it went at that speed. Again, what Heisenberg's uncertainty basically says here is the better you have that known, sort of the heading, sort of the speed it is, the less and less you actually know where the electron actually is. So again, there's an inherent uncertainty here. Heisenberg would actually write this. The delta x and the delta p is always bigger than they would use some constant here. And basically the notion here is you can't know sort of the position infinitely well. You can't have this totally decrease and the p is momentum or the velocity both well, because they both have to be bigger than a constant. The sort of, if you limit the if you can locate where the electron is, sort of the uncertainty in position here is low, the uncertainty in momentum will actually be increased. So this sun here is actually really strange. So far we've only seen one other thing in our universe that actually behaves like this, which is light. You ever heard of light duality? Light can sometimes be thought of as a particle, as little packets of energy, as little photons. Right? We had talked about electrons, especially when they fall. They release these packets, these photons of energy. They carry this energy away. Or light as a wave can actually carry energy from place to place. The color of light actually depends on how much energy is actually carried. So in this case here, we're just sort of likening electrons similar to what's called the duality of light, this dual nature of light. It can be a particle or it can be a wave. Electrons can be understood or can be thought of as a particle. Right? We've been very comfortable with that one here. Well, it's a subatomic particle. It makes up part of the nucleus here. Particles here would have mass. So we can think of, in the light case here, it's actually photons. In this case here, well, it's actually electrons. Maybe electron has mass. Right? Particles have mass. Particles will have momentum when they collide with things here. We can think of it as a particle, or we can think of it here as a wave. Now this one here we completely don't have any exposure to, because I thought of electrons as a single dot, right? I think of something that I can actually find, but given Heisenberg's uncertainty, given that as this inherent intrinsic unknown to it, what the electron is doing is actually behaving in its wave nature. For its wave nature, I'm just going to introduce to you something called the wave function, and we're just going to use a very fancy symbol here called psi. That's another Greek letter here. Basically, it's like a math equation, and it tells this electron what it can do, how much energy it has, what's the spin, how far away from the nucleus it can get. It's basically an equation to describe that electron. Every electron will have its own different wave function. Even the orbitals themselves will have a different wave function as well. To start us thinking about the strangeness where electrons can actually behave as a function, we're going to use the Schrodinger cat analogy. It was said that Schrodinger did have a cat. As you heard from the Big Bang Theory episode, I'm glad he didn't do this experiment on his cat. So, just as an analogy here with Schrodinger's cat. Schrodinger's cat. This is just a thought experiment here. This was in the early 1900s when quantum theory was first developing. This was Schrodinger's way of trying to explain this wave nature of electrons, what the electrons are actually doing, what are the S, P, Ds, and Fs supposed to be. So, the experiment goes here. Schrodinger took his cat. So, we have a happy cat here. Right, so, there's my cat. And basically, he puts his cat here underneath a box. Now, unlike what I drew here, the box here isn't transparent. You can't actually see the cat underneath. Maybe it's a cardboard box here, so you can't actually see the cat underneath. The cat is actually, unfortunately, put under the box here with a sealed vial of poison. In the Sheldon's explanation, it says this seal poison here would explode at some random time. Or you can think of, well, imagine there's a nice cork stopper on the top here. You know, cork does form a good seal, but it's not always 100%. Give it enough time, the poison will actually seep out. So here goes the experiment. So we have Schrodinger's cat. We put him in under the box here. We have our poison. And the question that he frames is, as long as the box is over top of the cat, I want to ask the question, is my cat dead or alive? Which one is it? Is my cat dead or alive? Let's think about the option. Why might my cat be dead? Well, my cat will be dead if the poison has broken out, if it's leached through this sort of cork lid here. Cat smells the poison here. Oh, we have a dead cat. Boo. Right? Why might my cat be alive? Well, even though the cat unknowingly has a vial of poison beside him, as long as that poison here has not been exploded yet, the cat here is totally oblivious. The cat here is still alive. So, in some sense, I'm answering the question, well, is my cat dead or alive? I really don't know because the box is over top of it. Instead of just leaving it like that, just saying, oh, yeah, it's unknown. I don't know, cat dead or alive. I'm actually thinking of the cat in this funny quasi state here. He can be thought of as actually both dead and alive, which is a little bit strange because we would say, wait a second, dead and alive are opposites. You're either one or the other. But in my way of sort of telling you, well, I really don't know, I'm sort of saying the cat is in this funny state here. He could be dead, he could be alive, he could be both. And basically the understanding here is, as long as the box is over top of the cat doesn't need to decide one or the other. How would I know for certain? Well, I would know by doing an experiment, by taking a reading. And what I want to see is, is my cat dead or cat alive? But in some sense, when I go and I lift off the box, as I lift off the box here, the cat somehow realizes that. The cat says, oh shoot, I can't be in this dead and alive state. Those two are opposites. I either need to show you, oh yeah, I'm still alive, or I'm dead, right? The cat only needs to decide when you actually take a measurement. So electrons actually have this really funny principle as well. Electrons are like this cat underneath the box. We've been thinking of electrons here as particles for a long time. They have to be somewhere. They have to be doing something. But in their wave nature, like this cat, the electron really doesn't need to take on any spot, doesn't need to take on any velocity until you're going to look for it. When you go look for it, you take off this metaphorical box, the electron somehow knows an observation is being made, and only then the electron then takes up a position. So, using this analogy and linking it to electrons here, electrons, like this cat, electrons don't take on any position or velocity for that matter, right? They don't need to take on a spot, they don't need to take on a speed until a measurement is made, until you go looking for it, until you ask a question, well, what is the electron doing? Where is the electron? And in this analogy here, it's like you going, oh, I can't bear it anymore. I need to go lift off this box here. In some sense, by lifting off the box, I've screwed up the system. Because earlier, when the box was over top, the cat could be in this funny dead and alive state. By taking that observation, the reason why quantum is so weird, somehow the electron knows it's being looked for. And when it knows it's being looked for, only then does it take on a location. It takes on a spot. So far this SP, D, and F, those placeholders I've been saying, we've been calling them orbitals, right? So these orbitals here, those S, P, D, and F, right? So you can think of the language here, energy level, sublevel, energy shell, subshell, orbit, orbital, so sort of the little bit more detail. These orbitals are essentially, they're places or they're regions where your electron is likely to be found. It's a place where the electron might pop up. And if you want to get into the real details of this one here, it is taking that wave nature of the electron, right? Just like functions can go into the positives or into the negatives here, this wave function, as represented by this psi letter here, because I'm actually plotting a region of space here in the sort of positive Cartesian system here, what I want to only plot is only positive distances. The easiest way to make something positive is just to square it. So what's going to happen is I'm going to take my wave function. This guy by itself could have been positives or negatives above the axis, below the axis, but upon squaring it, we end up getting everything positive, And in that case there, that's what this orbital is. We refer to this orbital here as a probability distribution. Probability distribution. So there's just a good chance of finding my electron somewhere in this shape that I mark off for you. Another analogy for you here, let's say I notice, oh, I lost my keys, right? Well, obviously I need them, right? So I'm going to go looking for them. I would go looking at places where I've been to, right? I check my jacket, I check my bag, right? Those are higher likelihood of finding my keys. I wouldn't go somewhere where I haven't been today because the chance of finding my keys there is actually very low. Same idea here. The orbital marks off spaces that you might find the electron, but there are other areas that are not as likely here. I wouldn't typically look in that area. So what I'm going to do for you here is I'm actually going to sketch out for you in this lesson here the S and P orbitals, and then I'm going to link you to a website where you can actually look at some of the other orbitals. We will come back and look at the d orbital shapes back in chapter 3 as well, but they are going to start getting more and more complicated. Even though the shape is complicated, just keep this big idea in mind. It is marking off a region of space. It's marking off an area where the electron might end up appearing. So, in starting you off just sort of thinking about drawing these diagrams here, let's start off with a regular sort of XY plane, right? We're used to plotting a graph like this. Let's imagine this is our graph paper. Let's imagine taking this piece of paper here and just putting this paper flat. So we have, let's say, X going this way, Y is actually going in and out of the page here. This one here will allow me to get a Z axis out of it. We stare at that for a little while here so you can start seeing that in 3D. Basically, I'm going to start drawing shapes here, marking off what does an s orbital look like or a p orbital look like. They're all regions where the electron might appear. An s orbital here is still fairly boring. An s orbital here always looks like a sphere. So let's do as an example here. Lithium has a configuration here 1s2, 2s1. Right? So let's try to draw out the 1s orbital. Because I told you an s orbital is a sphere, it's like a sort of like a soccer ball size shape. Let's imagine the nucleus is in the middle, right? There's no doubt of sort of where the nucleus is. But what I'm marking off for you here is there is a region of space, almost like a soccer ball size shape here. There's a region of space where there's a good chance of finding that electron there. This one here really would be like a sort of dotted diagram here. This was that probability distribution. This is that I have a good chance of finding my electron there. Notice that there are no walls on this container. It's not like you're stuck inside a room and you can never leave. It's just that if you go too far out of this sphere here, the chance of you finding the electron somewhere out here is a lot less. So it's a lot higher likelihood in here. That one there so far may be, let's say, a 1s orbital. So what I'm saying here is for lithium, when we've been saying with the configuration 1s2, we're saying the electrons should be found somewhere within that shape. Just like the cat doesn't need to decide whether it's dead or alive until you go looking for it, the electron really doesn't need to take on any spot, any velocity or anything like that. When you go looking for it, the electrons somehow realize and they say, oh, someone's looking for me. Oh, I'm actually over here and I'm actually over here. So the electron actually only takes on a particle nature when you've in some sense screwed up the system by going to look for it. When you look away, the electrons sense that as well. Again, it begs the question, how do electrons know? But electrons here, they really don't need to take on any shape, just like the cat doesn't need to decide dead or alive until you make a measurement. When you make a measurement, you've screwed up the system again. The electron sort of pops up, oh, I'm actually here and I'm actually here. As we start going from shell 1s over to shell 2s, what's the difference between shell number 1 and shell number 2? Well, the simple Bohr model would just say, well, shell number 2, energy level 2, this main energy level is actually farther out from the core. Shell number 2 will also be a spherical shell. I'm going to color code it for you, let's say in green. And basically what's plotted for you here is there's a good chance of finding my electron somewhere out here. So when you go looking for it, because I have one electron in my 2s, I should see one electron pop up somewhere here. And it's only popping up because someone has gone to look for it. So instead of this more simple diagram where electrons are just in orbit, right, like planets around the solar system, what we've done here is we've actually marked off a region of space, a likelihood of where we might find the electron, and have this funny interpretation. The electron really doesn't take on a spot until you actually go looking for it. Let's get to one more interesting case here, those p orbitals. Remember the p orbitals here, typically we're going to call them dumbbell shaped. It's like a weight at the gym. Whenever p orbitals show up here, they always come to us as triplets. We can actually write them down px, py, pz for the 3 different coordinate systems here. Dumbbell shapes here are sort of larger on the ends and they get more narrow where you actually hold them in the middle. If I plot a sort of 3D coordinate system again, so again x, y, z, if I can color code this for you here, let's say px, a dumbbell shape here would be like a weight, right? It's actually sort of larger on either side, but not very large on the middle. Again, this one here would be a probability distribution. It's not like a really hard wall or anything like that, but it's just where the electron might end up appearing is somewhere within this shape. Careful, this dumbbell itself is 1 p orbital. So even later on, let's do, say, oxygen's configuration. Let's say we have 2 electrons in this px orbital. This lobe, this 2-lobe system, this whole dumbbell is 1 p orbital. So either both electrons are going to appear over here, or 1 electron appears here, 1 electron appears here, maybe both electrons appear here. In total, it can only have 2 electrons. That's what Pauli guaranteed. How does the py compare here? You guessed it. Py is a dumbbell here that's in and out. Again, sort of the probability distribution. The shape is a little bit different, but again, the understanding is the same. Like the cat underneath the box, the electron doesn't need to decide on a spot or a speed, but when you go looking for it, the electron has to somehow notice and then appear somewhere. So far I have 1 electron in the py, so maybe 1 electron pops up there, and let's do one more here, which is a pz. Sorry, I wanted to color code that there. Let's say your pz here and up and down. The pz also a dumbbell shape, also sort of large on the ends, and basically it doesn't need to take on a spot until you go looking for it. When you go looking for it, the electron has to appear here. I want you to take a note here for the S and Ps. You definitely need to know the names of these shapes here. These 2 are considered outer electrons or outer orbitals. And like I mentioned, these ones here are your valence shell or valence electrons. So when you did your Bohr model, when you said first shell holds 2, second shell holds 8, third shell is it 8 or is it 18? The 8 always refers to the S and the P electrons. The D electrons and the F electrons, although they belong to a certain energy level, we're going to see spatially speaking they're actually a lot closer to the core. Let's say, so my D orbitals, let's compare, let's say a 3s orbital, 3p orbital. There's actually parts of the p orbital that will actually be even further out. So 3p orbital, those are 3 individual orbitals. If I actually had a 3D, I had to get up to floor number 3 before I started getting to my Ds. We'll get into their shapes in a later chapter. But the Ds are held a lot closer to the core, which actually is why when I come to pull off electrons as cations, if I have p electrons, there's places on the p orbital that are farthest out. Those would be the first things that I pull off. Only once all the p's are gone, then I attack the s's. Those are the next closest. And then I work my way inside. Only when those are all gone, then I attack the d's, if not the f's afterwards. So let me switch over now. I'm going to show you a nice website. I would encourage you to go stare at some of these shapes here. So far, you just need to know the shapes of the S and the P's. The shapes are going to look crazy. They're going to introduce phase as well. But basically, the understanding is the same. It's marking off a region of space where the electron might likely appear. So let's just switch over now. Okay. So this is the website that I was mentioning here. It actually does give you some more observations of actually isotopes and some of the properties. In this one here, I just want to show you their orbital pictures. So just like before, we have the periodic table picture in front of you. What it allows you to do is you can actually hover over the different elements. In the middle here, it actually identifies for you the S, P, D, and F orbitals. It does a rough energy level diagram for you going up this way, and it also gives you the SPDF sort of configuration that we've been practicing. So let's just start off here with hydrogen. Let's keep things fairly simple. We talked about here, hydrogen here is an S block. It's the first electron in. It's going to be in a 1s1. S is a spherical subshell. There's basically like a soccer ball size orbital. Again, it's not very hard walls, but basically this shape, the electron can be anywhere within the shape here. It doesn't really need to take on a spot until you actually go looking for it. When you go looking for it, somehow the electron knows and the electron appears somewhere there. Helium here right beside it here would be 1s2, exactly the same orbital, but there's actually be 2 electrons that end up popping up. We just talked about lithium here. Now they are limited a little bit in terms of the size, the area that they have here, But if you just remember that the orange ball is this large here, now if that orange ball were the same size, the blue orbital is actually larger than the orange ball, just like shell number 2 is actually farther out than shell number 1. When you go looking for it, our configuration is the 1s2, 2s1. 2 of them should appear in the orange, and then 1 of them should appear in the blue. Again, just like the cat doesn't need to decide dead or alive until you actually go looking for it, the electron doesn't need to appear until you go looking for it. So 2s1, 2s2, no change there. Let's go over here to 2p. So don't worry too much about the blue and orange. That actually refers to the phase of the equation. So this is a wave function, just like any equation can go positive or negative. One of the colors marks the positive, one marks the negative. Here, we're going to take the square of it anyways because we're in a positive area. So that way it just sort of marks off a region, a probability where the electron is likely to be found. As I skip over from 2px, 2py, 2pz, as I do our Hund's rule, I just want you to note the orientation of this diagram. So 2px, 2py, 2pz, you notice they're all 90 degrees from each other. As I go back, it's going to then be, again, 2px, 2py, 2pz. Now let's go through shell number 3, right? So now basically a ball and a ball and a ball, right? And getting farther and farther out, we have the configuration that we can always compare it to. Basically, the electrons should end up appearing when you go make an observation. So we have 3 shells out. As I get into 3p's here, the dumbbells used to be this size. Now imagine a third shell of dumbbells. So it's like a dumbbell and a dumbbell. Again, don't worry about the blue and the orange. This one here is just one shell, maxes out at 2 electrons apiece. So I go in px, py, pz, px, py, pz. It's only the s electrons and the p electrons that are considered valence. So when I get to potassium and calcium, so far I'm going to have just a spherical shell, and now I'm going to be 4 shells even further out from the core. The Bohr model sort of breaks down by about calcium because when you get to scandium, scandium needs to have 1 extra electron, but that extra electron is not a valence electron. It's actually one of those inner d electron shells. Your d orbitals here will typically look like butterflies. More on this in chapter 3. Again, don't worry about the blue and the orange. This butterfly actually has 4 lobes, 4 areas, but notice that this is just considered 1 d orbital. So when Pauli says an orbital can hold 2, they can have 2 electrons in all 4 of these lobes here. As I go through the butterflies here, so butterfly, we have one that's 90 degrees off from it here, one of them that's just totally fancy shape. These are all solutions to what's called the Schrodinger equation, in honor of Schrodinger and his cat and all that. But basically, you can see the configuration. We go through D1, D2, D3. Remember, we said chromium was an exception. Instead of being an S2, D4, it would rather have promoted its S electron. You see that here, 1 S electron, and actually promoted it into the D5. So that's going to be D5, D5, and then you backtrack and you go back through the d orbitals there. As you keep going through there here, you can get sort of a butterfly and a butterfly, so the drawings get to be a little bit more crazy. Again, the shape is completely different, but again, the understanding is the same. Basically, it's marking off a region of space that when you go looking for it, the electron should appear in there. The electron, like the cat, doesn't need to decide dead or alive until you make an observation. The electron doesn't need to take on any spot until you lift off the box. I'm just going to show you roughly what the f orbitals look like. I'm not even going to try bothering drawing them there. We get our f orbitals here. You'll notice on this periodic table, they actually pulled out lanthanum and actinium as your first f metals. Pretty much by the time you get to the bottom part of the periodic table anyways, they're getting so many exceptions anyways, it's hard to draw. For our periodic tables, lanthanum and actinium were the first d metals, so I would still go 5d1, 6d1. I would go through the 4f14, fill in all 14 before you come back, fill in 5d2, 5d3, 5d4, and whatnot. So just to show you a rough picture of the f orbitals, again, don't worry about the orange and the blue, but basically it's marking off an area of space where the electron might end up appearing. And I go back through and I go just pair up all those f electrons. Whenever the f show up, they come as 7 rooms. 2 electrons apiece means 14 going across. As I go lower than that here, I go just one farther shell out. Just gets to be a lot more complicated in terms of the shape. The configuration is getting to be really long. You see the configuration here in that corner for this bottom here is getting really, really large. But mainly I want to focus in on the orbital shapes. The orbital shapes here mark off sort of where the electrons might end up appearing. Right? So play around with that simulation a little bit here. Definitely be able to practice writing the configuration just with the periodic table, doing it on an energy level diagram. They might ask you questions like how many unpaired electrons there are, is everything paired up, and specifically what the shapes of the S's and the P electrons are. S's are spherical, and then P's are dumbbell shaped. Right? So if you have any questions, just let me know. Thanks, guys.